All right, so it's my pleasure and I'm very excited to be here. Thank you, Miklos, for the introduction. Thank you all for coming. Today I'm going to show a very exciting result, a classical result that has many applications, and the proof is very interesting and non-trivial. So let's start. So this is some reading of the original paper by Martin. Is good reading. And there's also a book in preparation, which I don't know whether it's available already, but at some point it will be. And for those who have access to the book, I'm going to cover chapters 1 and 2 of the book. So what is a game in this talk? So we're talking about, as Miklos said, alternate move games, and not only alternate move, but also we have a winning set. But in this talk, I will just call it a game. Okay, so this is a game. What is a game? The game is played in moves, and in the first move, player 1 takes the move A0, then player 2 plays A1, and then A2, A3, and A4, and so on. And there is a certain set, which we denote by capital A, and if the entire play, the infinite play, happens to be in that set, then we say that player 1 wins. And if not, then we say that player 2 wins. So this is the model. Now some slightly more formal definition of what I've just said. So the moves of the game, they belong to an arbitrary set. I usually don't mention this set. It can come from any set. It doesn't have to be finite or countable or any cardinality or any structure, just a set. And finite sequences of moves are called positions. A position is, in game theory, we sometimes call it a history, a finite history. So it records the moves. And there's a certain tree of positions, which we denote by T. And this is it describes the game, the collection of all possible positions. So not every sequence of moves is a position. The tree of the game describes what are the possible positions. And we have two conditions. One is that there are no terminal nodes, namely that every position has an extension. Every position, we can find a longer sequence of moves, which is also a position. And the second condition is that if a certain sequence is a position, then all the prefixes of that position are also possible positions. So this is what defines a tree. And a play is just an infinite sequence of moves whose finite prefixes are all positions. So it's a branch of the tree. An infinite branch of the tree, and we denote it by T with square brackets around it. And a game is just a pair, a tree, and a subset of the plays, which we call the winning set. And we usually denote the tree by T and the winning set by A. And the meaning is that player 1 wins if the play is in A, and player 2 wins if the play is in the complement of A. Okay. Now some more formal definitions. What is a strategy? So a strategy of player 1, for example, is just a mapping that maps each position at an even level of the tree to a move that leads to a position, to an available move at that position. And the same thing for player 2. Player 2 plays after plays at positions of odd length. And a pair of two strategies, one strategy for player 1 and another for player 2, induces a play, a sequence of moves, an infinite sequence of moves. And we say that player 1 wins if the induced play is in A, in the winning set. And player 2 wins if the induced play is in the complement of A. So for every pair of strategies, there is a winner. One of the players wins. But it doesn't mean that the strategy of that player is a winning strategy. A winning strategy is a stronger condition. A winning strategy is a strategy that wins against any strategy of the other player. Or equivalently, a winning strategy is a strategy such that all the plays which are consistent with that strategy end up in the winning set of that player. If it's player 1, it's the set A. If it's player 2, it's the complement of A. And a consistent play or a consistent position is just a play or a position that agrees with the moves of that strategy. And a game is called determined if one of the players has a winning strategy. Either player 1 or player 2 has a winning strategy. And just I want to make sure that we see that not all games are determined. Okay? It's not an empty definition. So there are some games which are not determined. I'm going to show you one such game right now. So we're going to use the axiom of choice to construct this game. It's not that trivial, but it's not very complicated. So the tree of the game will be the complete binary tree. So it is composed of all finite sequences of zeros and ones. And the plays of the game are just infinite sequences of zeros and ones. And just notice that the cardinality of the set of plays is Aleph, it's the continuum. And also the cardinality of the sets of strategies of the players. We're going to denote the set of strategies of player 1 by S1 of T, and similarly for player 2. So the cardinality of the set of strategies is also the continuum, because a strategy is just a function from positions to zeros and ones, to moves, and there are countably many positions in this game. So the cardinality is Aleph. Since the cardinality of the set of strategies is Aleph, the cardinality of the union of the sets of strategies for player 1 and 2 is also Aleph. So there is a one-to-one mapping, a bijection, not just one-to-one, a one-to-one and onto mapping from Aleph, from the first cardinal, the first ordinal of cardinality Aleph, to the set of strategies. We're going to use this mapping, this bijection, for the construction of the game. So what I have to construct now is the winning set. Right? So this is how I construct it. First, I'm going to construct an injection from Aleph to the set of plays such that X of alpha is going to be consistent with the strategy S alpha for every alpha smaller than aleph, for every ordinal smaller than aleph. And how I'm going to do it? I'm going to do it recursively, and this is possible because the number of consistent plays also has the cardinality aleph, which is greater than the number of plays that we've already chosen, which is the cardinality of alpha, and therefore there always exists a play which is both consistent with the strategy S alpha, and it has not been chosen previously. And here I use the axiom of choice by choosing this specific X alpha. Now I set the winning set to be all X alphas such that the strategy S alpha is a strategy of player 2. And why is this game not determined? Suppose player 1 had a winning strategy, then that winning strategy must be some S alpha. But as you can see, X alpha of that strategy is not in A. So so X alpha is consistent with S alpha, but it is not in A. So S alpha cannot be a winning strategy. And now suppose player 2 had a winning strategy. Then let's say that strategy is S alpha. So X alpha is in the set A, because S alpha is the strategy of player 2. And this means that that S alpha is not winning, because X alpha is consistent with S alpha, but it ends up in A, which is not the winning set of player 2, it is the winning set of player 1. Okay, so this is the example. All right, so now what are we looking for? We're looking for classes of games which are determined, which we can say that they are determined. Let me give you some examples of such games. So one example are games in which the identity of the winner is known after a bounded number of stages. So these games are determined, that this is an interpretation of Zermelo's theorem. So there are some debates about what Zermelo's theorem is, but let's say that this is Zermelo's theorem. It says that if the game has a finite horizon, then it is determined. One of the players has a winning strategy, and this can be done by backward induction. And by the way, last week was Zermelo's 150th birthday, just for your information. And now another example is a game where the identity of the winner is known after a finite number of stages, not necessarily bounded, but after any play of the game, there is a certain stage in that play at which stage it is already known who is the winner. Okay, these games are going to be called Klopen games. Klopen means closed and open, and I will explain what this. It should come from some topology, and I will show you what this topology is. And another class of such games, of determined games, are games in which any win of player 1 can be identified after a finite number of steps. And these games are called open games, and the equivalent thing for player 2 is these games are called closed games. All these classes of games are determined, and I'm going to prove it in this talk. And obviously, this is not the main theorem that I'm going to present. These are just warm-up statements. So now when I said open and close, I want to define a topology on the set of plays. So I need a few definitions. A subtree of a tree is just a subset of the tree. So it's a subset of the position, which is by itself a tree. So it doesn't have terminal nodes, and it doesn't have, and every position, all the prefixes of that position are also in the tree. So this is a subtree. And there is a special kind of subtrees. You just take a position P, and the tree TP is a subtree of T that consists of all the positions which are comparable with P. So either extensions of P or prefixes of P. This collection, and P itself, this collection of positions forms a subtree, and it will be important for us. The set of plays has a certain topology. The basic set of this topology are the collection of paths of the trees TP, where P is a position. So you just take a position and you look at all the plays that go through that position. This is a basic set. Okay? This is also known as the standard product, Tikhonov product topology of plays. Okay? So this is a basic open set, and an open set is just a union of such basic sets. And now that we have a position, a topology, we can talk about open, closed set, Klopen sets, which are sets that are both open and closed, and also Borel sets with respect to that topology. The Borel sigma algebra is the sigma algebra generated by the topology. Okay. So now this is the main theorem. The main theorem says that all Borel games are determined. So if the winning set is a Borel game, so as you can see, this is a generalization of all the bullets that I've shown you before. So when the winning set is a Borel set, then the game is determined. And in the examples that I showed you, there were all examples where the winning set was either open or closed or Klopen, and some variations of that kind of sets. So this is going to be the theorem that we're going to prove today. Now for a warm-up. So this is a theorem by Gale and Stewart. And this theorem that says that if the game is closed or open, then it is determined. So if we know that the game is determined, then if we take the complement of the winning set, it will also be determined. This is just an easy exercise. So what I'm going to prove here in this paragraph is that closed games are determined. Okay? So this is the proof. And actually it's nice. Sometimes I teach it when I teach game theory, and we teach Zermelo's theorem in one of the first lectures. I show them that you can generalize it to this result where the identity of the winner of only for one player, that if that player wins, then it is known after a finite number of steps. So it is a generalization. Let me show you the proof. Okay. So if player 2 has a winning strategy, then we're done. So suppose player 1 does not have a winning strategy. And now we define a winning strategy for player... If player 2 has a winning strategy, then we're done. So suppose player 2 does not have a winning strategy. So now we define a winning strategy for player 1 as follows. Player 1 always tries to avoid positions from which player 2 has a winning strategy. So this is what player 1 does. And since the complement of A is open, if player 1 does not win, it means that the play is in the complement of A, which is open. So there is a certain position after which any extension is in the complement of A. And this is a contradiction because we've just reached a position in which player 2 has a winning strategy. So by avoiding entering positions in which player 2 has a winning strategy, player 1 can actually guarantee to win the game. Okay, that's the end of the proof. Questions? By the way, you can interrupt me anytime you want. You can unmute and interrupt me. Okay. So this is Gale and Stewart. We're going to use it in other parts of the proof. So now let me talk about Borel sets. So I'm going to use the hierarchy of Borel set, not just the sigma algebra of Borel sets. So Borel sets can be defined recursively. So the first, I'm going to define a sequence of collections of sets, sigma alpha and pi alpha. So sigma 0 is just the open sets. It is the topology. And for any alpha, pi alpha are just the complement sets of sets in sigma alpha. And for alpha greater than 0, sigma alpha is going to be all countable unions of elements from pi beta, beta smaller than alpha. Okay, so this is a way to construct the collection of sets such that in the end it will be close to the operation of taking the complement and countable union.
Ron, did you mention that the alpha and the beta are ordinal numbers that you're doing with?
Yeah, the alpha and beta are ordinals, yes. Yeah, you can do it for any ordinal. It is defined for any.
Oh, yes, I just didn't hear you saying ordinal numbers, and therefore.
Yes, that's true.
I was hesitating if the others know it. Yes.
Yeah, so I think in this talk, alpha and beta will always be ordinals, but yes, I didn't mention it. Thank you, Abraham. So I do it for any ordinal, and if I take the union of sigma alpha for every countable alpha, you can see that what you get is a sigma algebra. And this is the Borel sigma algebra. You can never go out of the Borel sigma algebra because all the operations that you make here are operations of the sigma algebra, so you cannot get out of it. But after you covered all countable ordinals, then you already have a sigma algebra, and this is the Borel sigma algebra. And for a certain set in the Borel sigma algebra, we can take the least alpha such that that set is in either in sigma alpha or in pi alpha. This is called the Borel level of the set. So now we have a certain hierarchy of Borel sets. Not all Borel sets are equal. Some are more complicated and some less complicated. And I'm just mentioning that if I take a continuous function, then the inverse image of that continuous function preserves the Borel level. Or at least it does not increase the Borel level. So it's not true. It shouldn't be is the Borel level. F minus 1 of A is at most of Borel level alpha. Okay, it can the inverse image can be of lower Borel level, but not higher. Okay. So these are things that you can verify yourself. These are quite standard things. Now we're starting the proof. Okay, we're starting the proof. It's a long proof, a complicated, very technical proof, but a very nice one and an elegant one. And a key notion that is going to be used all through the proof is the notion of a covering. So what is a covering? A covering of a tree T is a tuple, T, pi, phi 1, and phi 2. Okay, so tile T is a tree, and pi is a function from the covering tree to the covered tree. And this function has to be monotonic with respect to the extension relation. So if one position extends the other, the image of those positions also extend one another, and it also preserves the length of the sequences. And phi I, for either I equals 1 or 2, is a mapping that maps the strategies of player I in the covering tree to strategies of player I in the tree T, such that the first n levels of phi I of a strategy depend only on the first n level of that strategy. Okay, so the fourth condition, which is the one that will be always be the hardest to satisfy, it is going to be the following. If I take a strategy of player I and I just map it by phi I to a strategy of player I in the covered tree, and then I take a play consistent with the image of tile Si, then I can also find a play consistent with Si itself in the covering tree, which is mapped to X. Okay, so this is what number 4 says. And we also say that if we have such a covering and we have a game, so the notion of covering does not involve the winning set. So if we do have a winning set, so now we have a game, T and A, I will say that T tiled and the inverse image of A under pi is a game that covers TA. Okay, so I also say that a game covers another game, not just a tree covers another tree. Okay. Now the skeleton of the proof. This is how we're going to proceed. So the first step will be to show that every Borel game has a closed and open covering. By a closed and open covering, I mean a covering such that the inverse image of the winning set is closed and open. The second part of the proof is to show that closed or open games are determined. Actually, we already proved it. This is Gale-Stewart's theorem. And the third part is to show that if the covering game is determined, so is the covered game. And number 3 is not very difficult. The difficult part is number 1. Okay, the first part. And we're going to prove the first part. So we're going to prove the first part by transfinite induction on the Borel level of the set. And actually the most difficult part will be the basis of the induction, the case where the game is closed. Okay, we're going to show that a closed game has a closed and open covering. So we already know that closed games are determined, but in order for the induction to work, we need to prove a stronger statement that says that closed game have closed and open covering. This is going to be the heart of the proof. And the proof of the first part is quite technical and long. I'm not sure I will have the time to complete all the details of it. I will leave something that there will be things that I will not get to, I think. Okay. Now some properties of coverings. First of all, the mapping pi is a continuous mapping. As a mapping of, so I said that pi is a mapping from positions to positions, but since it is monotonic, it extends to mapping of entire paths, entire plays, and as such a function, it is continuous just because the image of pi, the first n elements of the image of pi depend only on the first n elements of its argument. Another thing that we're going to use is that a composition of coverings is by itself a covering. We can compose coverings, we can compose the function pi and the functions phi I and get a new covering. So if I have, I wrote here, double tiled t covers tiled t, which covers t, then I can compose all these mappings and get a covering of t. I can show that double tiled t covers t with this composition. And the last property is the third element of the skeleton of the proof, which says that if I take a winning strategy of the covering game, then it is mapped to a winning strategy of the covered game. And this is due to the last property of covering, that if I take a consistent play, I can lift it up to the covering space, and then since my strategy is winning, it must be that play must also lead to the winning set. So that's the idea of the last bullet. Okay, so these things so far are not very technical. I didn't tell you all the details of each one of them, but you can work it out yourself, I believe. Okay, now we're going to try to approach the first element of the skeleton of the proof. And yes? Okay. To this end, I need further definition, the definition of imposed subtrees. So what is an imposed subtree? It is a subtree. So there will be two kinds of imposed subtrees. One is one imposed subtree or two imposed subtree. A one imposed subtree is a subtree that retains all the moves of player 2. So what does it mean? It means that player 1 in his positions can remove some of the moves, some of the alternatives. Okay, an example of one imposed subtree is just the collection of, you just take a strategy for player 1 and take all the positions which are compatible with this strategy. You get a one imposed subtree. But in a one imposed subtree, in contrast to a strategy, player 1 doesn't have to choose one move. Player 1 can choose any subset of his moves at any position. That's the difference, and the same thing holds for two imposed subtrees. Okay, another notion that we're going to use is unraveling. So if I have, so we say that a covering of a covering tile T, pi, phi of T unravels a set of plays A if the inverse image of A is closed and open. Okay, then we say that it unravels the set A. And of course, if a game can be unraveled, then it is determined, because closed and open games are determined. And now the key lemma is to show that any closed game has an unraveling covering. That will be the key lemma. And from there, everything works smoothly once you prove this lemma. And just a slight generalization of, we will need a slight generalization of K covering in order to apply an induction step. This is K covering. So what is a K covering? A K covering is just a covering such that in the first 2K levels of the game, it is the identity. So the trees are equal in the first 2K levels, and the mappings pi and phi I are all the identity functions in the first 2K levels. And now the key lemma translates to a more elaborate lemma. Any closed game has an unraveling K covering for every K. So the idea is, once you know it for K equals 0, so you know the key lemma, then you can apply it to any position at level 2K in the tree. You can apply it separately to the continuations of each one of these positions. And when you collect all these unraveling coverings, and you are forced to, in the first 2K levels, you are forced to play the identity, what you get is a K covering that unravels the closed game. Okay. Okay. And now another property of K covering is that it has an inverse image. So I'm going to explain what this thing, the picture that you see here, what it means. So first look at the bottom line of the diagram. So suppose we have such a sequence of covering. So T1 covers T0 with the functions pi1 and phi1 and so forth, so on. And not only pi1 phi1 is a covering, it is a k+1 covering. And similarly, pi2, phi2 is a k+2 covering, and so on. So I have such a sequence of k plus L coverings. So if I have such a sequence, I have an inverse image. What is an inverse image? I have a tree tiled T and functions tiled pi L tiled phi L, such that the diagram that you see here commutes, and each one of these coverings tiled pi L phi tiled phi L is a k plus L plus 1 covering. So if you look carefully at the diagram, you see that these are the numbers that I need. I need the the tiled pi L should be a k plus L plus 1 covering, whereas pi L need only be k plus L covering. And the proof of this lemma, of the existence of an inverse image, is as follows. So we actually, what we do a arrow chasing. So we are more or less forced to construct T tiled in a certain way. So first of all, notice that if we want to construct the first n levels of T tiled, it must be equal to the first n levels of Tn. Or maybe I missed Tn plus 1, something like that. Okay, so I'm really forced, the construction of T tiled does not have many choices. I have to construct it as I just described, and since the first n levels of Tn is equal to the first n level of Tm for any m greater than n, this is well defined. So this is how I construct T tiled. And now when I come to construct the mappings pi tiled, phi tiled, I'm also forced to do a certain construction, because because it has to agree with the mappings. For example, if I want to construct the first level of pi 0 phi 0, since it has to commute with pi 1 phi 1 and so on, and pi 1 phi 1 is it is a one covering, so I know that it is the identity, and then I compose it with pi 1 phi 1. So this gives me already the first level of pi 0 phi 0. Okay, is it clear? I will repeat it. Okay, so let's say that k is 0 for simplicity, and I want to see what is the first level of tiled pi 0 tiled phi 0. Okay, so when I look at pi tiled 1, phi tiled 1, at the first level of these mappings, it must be the identity, because it has to be a one covering. Okay, so it's the identity. And then I can I compose the identity with the mapping phi 1 pi 1, and by that I reach T0 in the end. Okay, so this composition forces me the definition of pi tilde 0 phi tilde 0. Okay, is it clear now? Yeah. Okay, I hope it is. Maybe not. But anyhow, by this arrow chasing, you are more or less forced to construct these mappings. You know that you have one arrow that has to be the identity, and the other arrow, the arrow to the left of it, is defined by composing two arrows. Okay. Okay, now let's piece everything together. So what I really owe you is the proof of the key lemma. But besides that, if you take it as true, then we are ready to piece everything together. Okay, so the first thing is to show that we want to show the lemma that if we have a tree, and a subset of plays A, which is a Borel set, not Borel game, Borel set, and K is an integer, then there exists a K covering of T that unravels A. So this is the first element of the skeleton of the proof, which is just stated here, but it is slightly more generalized than what we need, and this is often the case when we prove something by induction, that in order to apply the inductive step, we need to prove something a little bit stronger than what we really need. So this is what we're going to prove. That there is not just a covering that unravels the set A, but a K covering that unravels the set A. And the proof is by transfinite induction on alpha, the Borel level of A. Now, the key lemma already implies the case where alpha equals 0. Okay, so if the winning set is closed, then the key lemma tells us that it is unraveled, and the same covering that unravels a closed set also unravels its complement. So this is also the case when the winning set is open. Okay. And now we want to go to alpha greater than 0. So we know that A is a countable union of sets AN, and the Borel level of each one of these sets AN is strictly smaller than A. Okay, this is, or maybe it could be the case that A is in pi alpha, then it's the complement of something, but as I said, covering a set and its complement, or unraveling a set and its complement, is done by the same covering. So if A is not of that type, then the complement of A is of that type. So let's assume that A is a countable union of sets of lower complexity. So now we can apply the inductive hypothesis. And this is how we do it. So in the bottom line here in the diagram, I wrote the games. So in the first game on the left bottom corner of the diagram is T(A1). I consider this game, and by the inductive hypothesis, I have a covering with the tree T1 that unravels A1. Okay? So the mapping pi1, phi1 unravels A1. Now I look at the game T1 pi1 minus 1 of A2. So I take the inverse image of A2. As I said, since pi is continuous, the inverse image has at most the same Borel level. So now we can apply the inductive hypothesis again and get a covering that unravels the game T1 pi 1 minus 1 of A2. So this is the mapping pi 2 phi 2. And not only that I have such a covering that unravels one another, I also make sure that these coverings are K plus L coverings. Okay? So the mappings, as before, as in the previous diagram, the previous commutative diagram that I've shown you, these mapping pi L phi L are K plus L coverings. Okay? And now I know that there exists an inverse image. All these things has an inverse image. I can write the inverse image. And now look at tilde pi 0, tilde phi 0. This is a K covering of T. Okay? And now I argue that the inverse image of A is an open set. It is not a closed-end open set, it is just an open set. And why is that? It is just because this diagram commutes, and therefore it is the union. So it's the inverse image of A is the union of the inverse images of AN, and in what each one of the ANs is covered, is mapped to a closed and open set. The inverse image of AN is a closed and open set. And why is that? You just follow this diagram. So at some point, if you go from left to right, at some point you see that the set. I didn't write something correctly. So what I want to do, if you look here at pi 2 minus 1 of A3, it makes no sense. It should be the composition of pi 1 and pi 2 minus 1. So I take each one of the sets and push it backwards. So if I take AN, at some point it will be in Tn an inverse image of AN, and then at the next level it will be closed and open, and then when I take the inverse image of a closed and open set, I get an open set. So each one of the inverse image of each one of the ANs is an open set. So the union of these sets is also open. And now I can apply another step of the key lemma to get a covering of T tilde that unravels the inverse image of A, and so I get so that the proof is complete. Okay, the inverse image of I have a, so the key lemma says that the inverse image, that I have I can unravel a closed set, but the same covering also unravels the complement open set. So since the inverse pi 0 minus 1 of A is open, the inverse I can unravel it as well. And okay, so this thing completes the proof, I think. Do you believe it, or it sounds mysterious? Okay, maybe a little bit. Yes.
Maybe if you know, this is the inductive proof, that it's not the original proof of Martin, it's a second proof. Do you know the first proof? Can you comment on the essential differences?
I don't remember. I read it, but I don't remember. Sorry. Okay. So let's go to the proof of the key lemma. I don't think we will manage to go over all of it, but let's start. So the nice thing is that it gets more and the proof gets more and more complicated, and I will finish just at the point where I can no longer take it. So that is how it is going to go. Okay, proof of the key lemma. So we have a closed game, and we have to construct a covering that unravels the winning set. And we'll do it in 4 steps. Okay, so now we're going. So now we define we construct or define the covering of T. So first step is to define the tree that covers T. So we'll have tile T. The positions are of the following form. So it's the sequence that you see here: A0 T1, A1 T2, A2, and so on. This is a typical. This is how a typical position in T tile looks like. And now I will try to decipher the elements of this expression. So T1 is a one imposed subtree of the extensions of A0. So player 1 in the first step, player 1 takes a possible action in T, and also a one imposed subtree that imposes that first action, that first move. Okay? And player 2, so the intuition, or my intuition of this, I don't know, it's very hard to come up with an intuition because this proof is very surprising. And I will try to give my intuition. So my intuition is that player 1, if player 1 can, player 1 would choose T1 to be a winning strategy of T. If player 1 has a winning strategy, player 1 would choose it as T1. So this is what player 1 does in the first stage. Then in the second stage, player 2 plays, and player 2 chooses A1, which is... Yes? Player 1 chooses A1, which is a possible move in T1, and also chooses a subtree T2 of a subtree under the only restriction that the first move must be A0. So it's a subtree of TA0 with some further restrictions that I will mention soon. And finally, the sequence A0 to AN must be in T2. Okay, these are the rules of the game, except some further restrictions that I haven't mentioned yet. So this describes the possible moves in this game, the possible positions in this game. Now I'm going to give you the further restrictions. So in the second stage, when player 1 has two options as for how to choose T2. So we can do one of two things. This is again my interpretation. One is to surrender, and the other one is to prove that T1 is not a winning strategy, or is not winning, because it doesn't have to be a strategy. So to surrender, it means that player 2 chooses a 2-imposed subtree of T1, such that any play in T2 ends up in A. So he just surrenders. He says, okay, you want T1, I have nothing to do about it. I'm going to do something that I can do, which is imposing my moves, and then we end up in A. And the second alternative is to prove that T1 is not winning. And this is done by choosing T2 to be some TP for some position P in T, P has to be, the last letter in this sentence should be T1, not T2. So P has to be in T1, and it also has to be the case that after P, any extension goes to A, to the complement of A. So this is a proof that T1 is not winning. Okay, if T1 was winning, how can it be the case that I can find a position in T1 for which all the extensions are not in A? So this is a proof that T1 is not winning. Now, a point that has to be noted is that at this stage, player 2 always has an available move. It cannot be the case that player 2 cannot move, because if T1 was not a winning strategy or a winning imposed subtree, namely if there are some positions in T1 which are not winning for player 1, then it means that there is a play in T1 that ends up in the complement of A. And that, since the complement of A is an open set, there is a certain P such that TP is a certain P, which is a prefix of the play, such that TP, all the extensions of TP are in the complement of A. Okay, because an open set is just a union of basic open sets, so it must belong to one of these basic sets. Okay, so this is the description of the tree. Now I'm going to define pi, the mapping of positions. So this is very simple. You take a typical position, you just delete the trees. And you have a play in, you have a position in T. This is how pi is defined. As you can see, it preserves the length, and it is monotonic, and everything is okay. And you can also notice that that pi minus 1 unravels A, because telling whether the play in T tilde is in the inverse images of A depends only on the first two stages. Actually, it depends on whether player 2 surrendered or not. If player 2 surrendered, we know that the play, I will just go back one slide. If player 2 surrenders, then we know that the play will end up in A, and if player 1 does not surrender, then if player 2 does not surrender, then player 2 chooses TP, and from that moment on, the play must be in TP all the moves must stay in TP, and all the plays in TP are in the complement of A. So after knowing whether player 1 chose to surrender or to prove that T1 is not winning, we already know that that we're done. Just one thing to notice is that you cannot have player 2 cannot do the two options together. You cannot both surrender and play T2 just because one tree is in A and the other one is in A complement. So after the second step, we already know who wins. So this is a closed and open game. Okay. Now for the definition of phi1, which is a bit more complicated. So we are given some strategy in the covering game, and we want to map it into a strategy in T. So the first step will be, and let's say that the first step of the covering strategy is A0 T1. So the first step in the covered game will be A0. So now I'm player 1. I know that I should play A0. I play A0. And now I consider the following game. The following game, the tree of the game is T1, and the winning set is the complement of A, restricted to my tree. So in G prime, player 1 wants to be outside A. Okay? Player 1 wants to lose. Now, since A was closed, A complement is open, so G prime is an open game. Therefore, it is determined. So there are two cases. Either player 1 wins G prime or player 2 wins G prime, and the definition follows these two cases. So the first case, where player 1 wins G prime, so you define phi1 of, you define the following moves of player 1 as follows. So remember, player 1 has a winning strategy. So what player 1 is going to do is going to try to win G prime. Okay, player 1 tries to win the game G prime. He has a winning strategy, so it is guaranteed that player 1 will win the game. And not only will player 1 win, player 1 will also win after finitely many steps, because the game is open. A win of player 1 can be seen after finitely many steps. So there is a certain position in T1, so they play after a certain position in T1 is reached, from which all the extensions are not in A. And then they continue the moves of the covering strategy, assuming the history, the following history. Player 1 played T1 in the first stage, and then player 2 played this TP, and then they continue as it happens in this game. And okay, now the only thing to verify is that this is indeed it satisfies the conditions of covering. So we can see that the definition of, in this case, the definition of phi1 depends only on the first move until time p, and then it depends on the first n moves. So it satisfies the condition that the first n moves of the strategy are, of the covered strategy, are the functions of the first n moves of the covering strategy. This is okay. And if we have an X which play which is consistent with phi I of Si, then we can find the equivalent play in the covering set. The covering play is just the expression, the term written in the end of this paragraph. T1 and then TP and so on. Okay, so this is, it satisfies the condition. Now, a slightly more difficult case, it's the case where P2 wins the game. So, okay, so now let's consider T star will be the two imposed subtree of T1 that consists of all the winning positions of player 2 in the game G prime. So in the game G prime, player 2 has a winning strategy. So the initial position is winning for player 2, and so player 2 can always continue to a winning position, otherwise player 2 would not be the winner of the game. Okay, so as long as the game is in T star, as long as the game continues in T star, player 1 is going to assume that player 2 played T star, and then follow the instructions of S1, tilde S1, given that history. And if they continue without leaving T star, then it is guaranteed that the game will end up in the complement of A, right? Because the player 2 wins, no, in A. It is guaranteed that the game will end up in A. Okay, so we have to make sure that T star is indeed a legal move for player 2. So why is it a legal move? Because any play in T star is winning in G prime, which means it is in A, which means that it is indeed a legal move. This is the definition of legal moves. This is the first option, the option to surrender. This is a legal surrender move. So as long as they play in T star, player 1 assumes that player 2 really played T star and follows the instructions of tilde S1. And this, if they stay there, then the game continues. It is well defined. But once they get out of T star, then we are in a losing position for player 2, meaning a winning position for player 1, and this brings us back to case 1, where player 1 had a winning strategy, and then player 1 follows the instructions of case 1, trying to find a tree TP. So the last thing I'm going to do in the minutes that I have is to verify that this is indeed it satisfies the conditions of a covering. So let's see why it satisfies the conditions of the covering. First of all, the definition of the first n stages depend only on the first n stages of tiled S1.
Could you please maybe just remind the winning condition of G prime? I just got a little bit confused.
Oh, the winning condition of G prime?
Well, just its definition, maybe I just got,
okay, this is G prime. So G prime is it's a game whose tree is T1. So after player one chose T1, they focus on the tree T1. But now I switch the roles of the players. Player one wants to be in the complement of A instead of A. This is G prime.
Yeah, thank you.
Okay. So now we want to verify that the first n stages of phi 1 in the second case, that the first n stages of phi 1 of tiled S1 depend only on the first n stages of S1, but you can see it here in this expression that there are certain periods in the life of this definition. In the first period, when they are in T star, then you can see that they follow T1 step by step. So they always depend only on the nth steps depend only on what happened before time n. And after if they left T star, after they left T star, then they no longer follow the history. They just trying to follow a certain path. They follow a winning strategy for player one in G star, which does not depend at all on the next steps of S1. But once they reached the position P, from which it is guaranteed that the play is not in A, they continue following S1 as if the history was of the length of P, as expected. So this is not a problem. So the only thing remaining to verify is that you can lift any consistent play. So if you just take a consistent play, so in the end, it will the consistent play will either end up following T star, then the lifting of that play will have T star in it, or it will switch to some TP, and then the lifting of the play will have TP in it. But in either cases, these are consistent plays with tiled S1, which are mapped back into the play in the covered game. I hope it's more or less clear, but these are things that can be verified. So I think my time is up. I'm happy to take questions if you have any. Of course, there is still step 4, which I didn't mention, which is the definition of phi 2. And as I promised you, it is even more complicated than the other steps, but I'm running out of time.
Thank you, Rani. Actually, you started a bit later, so you have some minutes, for example, 4 minutes for sure. that if you would like to say something.
It's very long and complicated. I don't want to do this.
Okay.
It will take me more than a few minutes.
Okay. Okay. Then any questions or remarks? Go ahead. Just unmute yourself and go ahead. Abraham, you unmuted yourself.
Sorry. Because I want to thank Ron for the talk, and I don't know if newcomers to this proof could follow on the first one the details of the proof, but I encourage, it will be recorded, so I encourage everybody to read it here or to read the original Martin's second paper, not the first one. Or it also appears in the book by Mertens, Soran, and Zamir, this proof, the inductive proof.
Okay, thank you, Merale. And thank you, everybody. I'll see you. Well, I stay here, but I will see you tomorrow.
Diti, you also muted yourself. Perhaps you have a question. Please go ahead.
We can talk during the break with Ron. So it's more like so this notion of covering. I mean, one was that when the image should depend on the values of the shorter prefixes. So it's like you don't look only on what you do along the history from which you came, but also other histories of the same. This is very much in the beginning for the covering.
In the definition of the covering, wait, should I go back to the definition of covering?
Yeah.
This definition?
Yeah, the first n levels, and only on the first n level. So 0.3.
Is such that the first n levels of this function depend only on the first n levels.
Yeah.
So now I didn't define what is an n level of a strategy.
Well, I guess it the first. Well, you restrict it to the domain of is shorter than no.
If you know what the strategy tilde S does in the first n days, or in all the positions of length at most n, then you already know what phi I of Si should do in positions of length at most n.
Well, so that was a question for the break. I mean, when does it happen that you look at histories that are not those history from which you're coming?
Sorry,
I mean, it is sufficient. I see.
We couldn't understand the question.
Okay. So you're depending on the entire subtree of depth n, or your low dependence on the subtree of depth to n, huh? and so it's like when you track the image, you had histories that didn't occur at all. I mean, for sure not. Yeah. So alternative histories.
Yeah, there are histories which are not consistent with tilde S1.
Yes. And well, I believe that you can need it. I would like to see when. I mean, what doing with histories that are not consistent.
Yeah, so I don't see. I see why I don't really need to depend on such histories, but I don't see why it makes any problem if I do depend.
No. It's certainly efficient. I mean, there's harm to require to have this requirement, and I have seen cases when it was really necessary, but then you had some imperfect information. Since you have perfect information, I could imagine that. I mean, the way on which you depend be smaller.
I will just make a comment. Yes.
I think if I try to understand, I didn't understand exactly the question, but if I understand the spirit of where Janos is looking at, is the issue that here it's a proof that there exists an optimal strategy. It doesn't prove, it doesn't argue to prove, but it probably could be adjusted easily, that it is a sub-game optimal strategy. Namely that after every finite sub-game, the strategy is still optimal. And for that, maybe one will have to make here some careful analysis of step 3.
Yeah. I think this idea with subgame captures somehow my intuition, but I agree it's not very clear. I mean, well, in my head it would be wonderful, for example, if you have if some things like conditions defined by automata, then VA would be nice to be user. Yeah, again an automaton that would not look transducer, only looks at the history so far, doesn't look at alternative histories. But indeed, I think that's what Abba is much more precise. I mean, we should depend on only coming from now. It should not depend on what you would have done other histories. Yeah. How you translate your strategy at certain graphics. But okay, this is really something.
Yes, so I think in the proof, in the construction, it really did not depend on inconsistent histories.
Yes, but I think the existence now, taking back what I said before, I think it's easy to prove that this result on the existence of optimal strategy proves basically, again by induction, the existence of a sub-game optimal strategy, namely that after every sub-game, including one that is inconsistent with your action, if you have the winning strategy, you play the still a winning strategy.
I will talk about this in day 2.
Okay. Yeah, let's come back maybe to it after Janos talk. Yeah. Thank you. Thank you.
Okay. Thank you all.
Thank you again.